Hello students, welcome back to Math 332 Elementary Linear Algebra. Today we're going to learn a new concept called inner products. Now before we go into the detail, I just want to remind you one of the main concept in this course was the concept of vector space, right? We started with Euclidean spaces like Rn, R2, R3, and Rn, right? And then we realized that a lot of mathematical structures also have the same feature as if they are the Euclidean space Rn. So we look at the polynomial of degree m 2 together with the addition operation and scalar multiplication. They essentially behave as if they are vectors in Rn. So all the concept that we developed for Rn, such as span, linear independence, and so on, can be expanded to the other vector spaces, such as vector spaces which consist of polynomial, consist of functions, consist of matrices. So we spent quite a lot of times looking at this abstract concept of vector spaces. And this is one of the very important idea in mathematics, which is generalizations. We look at a special case and then we generalize it to include more example, okay? And the concept that we're going to learn today, which is the concept of inner products, it's the same thing. The things that we try to generalize is dot products. So if you notice, we spend quite a lot of times on dot products, and dot products is only defined for vectors that is in Rn, right? We have dot products for vectors that is in R2, R3, so on and so forth. But they are all vectors for, the dot products is defined for vectors that is in the Euclidean space Rn. And we are going to look at what are the main properties for dot products. And it turns out there's only like 4 main, very crucial properties for dot products. And we want to generalize it. And we give it a new name for the generalized dot product. It's called inner products. And we want to apply these inner products to vector spaces other than the Euclidean space Rn. So that's the plan. So the plan is to look at the generalized version of dot products, okay? So that we can apply these dot products on vector space which consists of functions, for example, right? You take one function, you take another function, and we'll talk about the dot product of these two functions. We can't, right? We can't use the usual dot product to do it. So we have to use a generalized version of the dot product. It's called inner product. So we're going to investigate that. And other things I wanted to mention is that we spend a lot of time on dot products to develop formula for like the concept of projections, least square approximation and all that. And you will see that all this concept can be carried forward to these new inner products, okay? Just like the concept of spans, linear independence and all that was used previously on Euclidean spaces, but they are also valid on the other vector spaces, such as vector space consists of polynomial and so on and so forth. So we're going to see exactly the same thing on the idea that we developed using dot products can now be expanded to cover example with these new inner products. Everything is going to carry to the other space because essentially they are the same thing. Okay, we're going to make all this concept very precise, and this is all going to contain in this video. Okay. All right, let's look at the objective for this video. So at the end of this video, you should know what is an inner product, obviously, and you need to also know how to apply the least square methods in this new context. Now, before we go into the detail, let us recall one of the main concept, one of the main idea for this course. So if you recall, in the very beginning of the semester, we look at vector space, right? R2, R3, in general Rn. We study some concepts such as the concept of span, the concept of linear independence, and so on and so forth. And we realize that actually we can also find a structure such as a set of polynomial of degree m 2 together with polynomial addition and scalar multiplications. Seems like this thing right here somehow is kind of related to all the things that we know from what we call Euclidean space right here, right? So mathematicians spend a lot of times looking at one of the main properties for being in this Euclidean space Rn. That is to say, if you are in this Euclidean space, what kind of properties you enjoy, right? What do you have for being in Rn? And it turns out if you are in Rn, you'll satisfy 10 main properties, okay? And so we can say that, oh, okay, so if any kind of structure have that 10 properties, then it kind of behave as if they are in Rn, right? So this is a concept of generalizations. You look at Rn and you generalize, look at all the properties that define what does it mean to be in Rn, list them all out, okay? We have 10 of them, and we say that, hey, why don't we call anything that satisfy these 10 properties, which we call 10 axioms in the chapter called vector spaces, right? So we look at some of the stuff that looks very different from Rn, but as long as they satisfy that 10 main properties for what does it mean to be in Rn, then we will say that this is essentially like Rn, and we call this a vector space, right? So we generalize the concept of Rn to other types of structure, which doesn't look like very similar to Rn, but they are essentially the same. Essentially the same in the sense that the 10 property that Rn enjoy is also enjoyed by a structure that looks like this. So this is one of the main idea in mathematics, is called the idea of generalizations. You generalize an idea from this to some other stuff. So as we know in the concept of vector spaces, we not only have this, we can also look at functions, right? Together with their function additions and scalar multiplications. And this is also, again, very similar to Rn. In fact, they're essentially the same. And then we can also look at sets consist of order, let's say 2 by 3 matrices, together with matrix additions and scalar multiplications, right? And again, this is essentially the same as that. So this is the concepts that we know before, the concept of vector spaces. And from then on, all right, we can also refer to a polynomial as a vectors, okay? In this context, we can also refer to a function as a vector in this context, right? And so the concepts that we learn, such as the concept of span and linear independence, not only apply for Rn, but it's also apply for polynomial. It's also apply for functions. It also apply for matrices. And this is one of the main idea that we study in this course, the concept of vector spaces. All right, so what we're going to do is we are going to generalize the concept of dot product, just like how we generalize the concept of Euclidean space, right? So we've been spending a lot of times looking at dot products for the past few weeks, right? We look at the projections. We know that dot products can tell us about the angle between these two vectors, and dot product, if it is 0, the two vectors are orthogonal. We know a lot of things about dot products. And we wanted to expand these ideas so that we can also talk about dot products other than outside of the Euclidean space, such as R2, right? So for example, in R2, you have these vectors, 1, 2, take the dot product with 3, 4. We know how to do that. That's not a problem. That's 3 plus 8, which is equal to 11. That's fine. So now, since it's so useful, right? And we know that this is a vector space. We have other type of vector spaces, such as a polynomial of degree at most 2 with these additions and scalar multiplications, right? This is also a vector space, but we can't talk about dot products that is like this, because our polynomial doesn't look like vectors like 1, 2, and 3, 4. But because the dot product is so useful, we wanted to be able to extend that concepts to other spaces, like spaces such as the function space, right? This is also versions of a vector space. Can we talk about the concept of dot product? Can we generalize dot product so that it can also cover vectors that is in this space, so that it can also cover vectors that's in this space, so on and so forth, right? So we want to be able to extend the concept of dot products to cover things that is vectors in other type of vector spaces, but it's not necessarily a vectors that is in Rn. So how do we do that? Just like how we generalize vector spaces, the key thing is to look at the main properties for dot products. So if you look at the main property for dot products in Rn, we realize that there's actually not a lot of main properties for dot products. One of the main properties, one of the main features, so to speak, is that the dot products commute, right? U dot v is the same as v dot u. And we also do distribution a lot, right? We distribute vectors, distribute. So this is also one of the main properties. When you scalar multiply, when you multiply a scalar with this dot products, it is the same as you are taking this scalar multiplications and this dot product. This is also one of the properties for dot products. And also there's one more very important feature is the non-negativity properties for dot products, right? V dot V can never be negative. In fact, V dot V is the magnitude of V squared, right? So it's the length of that vector square. So length cannot be negative. So this one here has to be non-negative, right? It can be 0. And in fact, V dot V is equal to 0 if and only if the vector V itself is 0. So we look at it very, very closely on dot products, and we realize that these are the 4 main features for dot products. Okay, so this is the 4 main feature for dot products. If we want to generalize the concept of dot products, then it must preserve these 4 main properties, because this is what we do, right? If we have these 4 properties, the projection formulas and all those things should work, because in projection formulas, the orthogonality concept, and when we do all the computation, we distribute, we do this and we do that, everything is captured by these 4 properties. Okay, so now we want to expand. We want to expand and extend this concept of dot products to other type of vector spaces. For example, the spaces of polynomial of degree at most 2, right? Matrix spaces, for example. Okay, we want to talk about dot products, a version of a dot product for this space, right? Continuous functions, set of continuous functions with functions, additions, and scalar multiplications, so on and so forth. We have so many different type of vector spaces, and we want to talk about the concept of dot products for this type of vector spaces. So what we do, we generalize this 4 properties, okay? All right, so now this is going to get a little bit abstract, okay? So first, notations, okay? So first, notations. I'll talk about notations. So when we have a vector u that is in Rn, we have a vector v that is in Rn, right? So we can talk about dot product like this, right? So this is an operations between these 2 vectors. We can also have some other operations like vector additions, right? Scalar multiplications and stuff like that. So these are operation, right? So now I'm going to use the notations to denote a kind of operation, operations. So I write this. This is an operation, right? So this is a notation for an operation, just like this. It's strange because you never seen it before, but you will get used to it, because this is also a strange way of writing stuff, right? U plus V, right? Plus, this is an operation, okay? You get used to it because you've seen it so many times when you are little. You have 1 plus 2 equals to 3. So that's not a problem. So when I say U and then plus a V. So this is an operation, right? A notation for operation. And I'm saying that this is also a new notation for operation. So this is an operation, right? Okay, so this is, just remember that this is an operations of these 2 vectors u and v. What that operation is, we haven't said it yet. Okay, so it's just a notation of a sort of operation. Okay, all right. Now, so what we want to do now, once we know the notation and get comfortable with it, is that instead of talking about u dot v, right, in Rn's, and then to get a number which is in R, right? This is a real number. So instead of talking about this has to be in Rn, this has to be in Rn. Now we want to talk about an operations that is defined for U in a general vector space. It could be anything, right? So this could be polynomial spaces, right? It could be a polynomial space. It could be function spaces, matrix spaces, so on and so forth. It doesn't really matter. This doesn't have to be Rn anymore. So we take a vector is a generalized vector space. We take another one, right? We take another one, V, okay? That's also from a general vector space. Doesn't have to be Rn. And then we are looking at an operations, U bracket U comma V. This operations is called an inner product if this operation satisfies these 4 properties, okay? Now, this is an operations. If you do this operation in this manner, and if you do this operation in this manner, right? If they are the same, then we say that this operation has symmetric property. Okay? All right, have symmetric property. If you do this operation, if you take 3 vectors now, you take 3 vectors, U, okay, V, and W, right? U, V, and W. And let's say you do an operations u plus v and w, and if it is equals to u w plus v w, right, then we say that this operation has additive property. Okay, and same thing here. If this do operations by taking a scalar multiply u and then take the operation with v, if it is equal to this is called homogeneity property. Okay, and if you do the operations, with the vector itself vv, then if it is never negative, and this operation here, if it is 0, if and only if this thing here has to be 0, if you have that property, that is called the positivity property, right? Okay, so if your operations that you define, we haven't defined anything yet, but that operations, if you satisfy these 4 properties, then we will say that operation is an inner product. Inner products, okay, as you can see, because it satisfies these 4 axioms, these 4 properties, and these 4 properties is exactly the 4 properties for dot product. You see it? We are trying to capture the main properties for dot product. You see that? This is, if this operation is dot product, if this is u v is actually u dot v, this is actually a repeat of this. All right, and this is actually a repeat of this, a version of this. And this is actually a repeat of this, and this is actually a repeat of this. You see it? So we wanted to talk about an operations. If they satisfy these 4 main properties, we call that inner products. Because why do we call it inner products? Because we try to capture the main properties for dot products, and we capture it here like that. Okay, we capture it here like that. So this is any operations that satisfy these 4 properties will be known as an inner products. Okay, in that vector space, and it is a generalizations of the dot products. Remember, if you satisfy these 4 properties, this operation satisfy these 4 properties, then it is a generalizations of dot products. Okay. Okay, now we're going to leave these abstractions behind and look at a specific example. Okay, let's throw this behind, put all of this behind, and look at a specific example. Let's look at this vector space. Okay, let's look at this vector space V, which is consists of a set of functions that is continuous from A to B. All right, and together with the usual function additions and scalar multiplications, we already know that this is a vector space, right? We know that this is a vector space. It's not going to be a problem. Now we want to define a version of the dot products, okay? And I'm claiming that this, if you do this, if you take a function, right? This is actually from V, right? And then you take another function, which is also from V. Now let me define this operation as the integral from A to B fx gx. Let me define it this way, okay? And I am claiming if I define my operations bracket, right, the brackets f comma g, right, if I define my operation like this operations will satisfy these 4 properties. If I verify that it satisfies these 4 properties, what does it mean? It means that, okay, this is an inner product of 2 vectors that is from this vector space V. All right, what does it mean actually? It means that this operations is kind of like a dot product. In fact, it is a dot product in this generalized sense. It is a dot product. It's a version of a dot product. It's a generalization of dot product. This is kind of like you're taking a dot product, okay, of this 2 vector here, which lives in this new generalized vector spaces. Okay, now we haven't know that this is an inner product. It's a version of dot product yet until we finish verifying that it satisfies these 4 properties, because these are the property for dot products. If you satisfy these 4 main properties of dot product, it will behave like a dot product. You know what I'm saying? Okay. All right. So let's do the verifications. Okay. So first property, f comma g. All right. Bracket f comma g. That's by definition equal to this. And you know integrations. It's okay to switch the position of g and f. That's not a problem. And obviously that will equal to this. So this is our symmetric properties. It's no problem at all. It holds, right? Okay, let's look at the second one. You have this function f, bracket f comma g plus h. What does that means? Okay, the way we define this operation is this is, right, equals to the f, right? And then multiply this and then integrate from A to B. Obviously, we can distribute all this function. That's not a problem. And we also know that integral is linear. These are linear operations, so you can split them into the two of this. And obviously, this is equal to this, right? By definitions, this is equal to this. So the second property also hold. The additive properties also hold, right? So let's look at the third one right here. How about homogeneity property? If you have a scalar, C of f is this, right? By definition, this operation is defined like that, right? It's not a big mystery, okay? We have C of f and then g and then integrate. Obviously, you can take C out, right? And we get this. So we have this property also hold. This is homogeneity property, also hold. And the final property, okay, this final property here, if you take these operations with f and again with f itself, by definitions, it will be this. So think about continuous functions. If you integrate a continuous functions, right, like this, okay, so you have a functions, it's always f squared is always non-negative, and you're looking at the area, right? You're looking at the area from A to B, and it turns out the area obviously has to be non-negative, right? Because this is area, right? This, what does this mean? It means that if you have a function f, right? If you have a function f squared, this is a function f squared is going to be like this. They are continuous function. F is a continuous function, f squared is a continuous function. So there's no big surprise. It's going to be something nice, a nice curve like that. And we're looking at the area under this curve, So obviously it is non-negative. And if this area is 0, right? If this area is 0, then this function has to be 0 because we are talking about continuous function here. So if you have a continuous functions, right? Non-negative continuous functions, right? Non-negative continuous functions which have area 0, then the function itself has to be 0. All right, so the function itself has to be 0. So we see that if this thing here is 0, or your f has to be a 0 function, otherwise it would not work. You see what I'm saying? So now we have verified that these operations actually satisfy these 4 properties, right? Therefore, this is a dot product of generalized dot products for vectors that is in this space. They are obviously not typical column vectors. These are not. But if you do it like this, okay, if you do it like this, this basically is a generalized version of the dot products in this space. Okay, that's what. Now with this example, you look back. Okay, all these notations will kind of make sense now. The reason why they didn't specify anything is because there are many ways to define an inner product. So it doesn't have to be like this, right? A, B, and then something. It depends on what space you are in, and there are many versions of inner products, okay? So that's the reason why they go for this notation. I didn't really specify what's going on. But once you specify what is this means, right? Verifying all that 4 properties is not too difficult, okay? All right, so once we have the generalizations of dot products, right, which we call inner products, all the concepts that we have from before, for example, length, right, distance, orthogonality, all this thing that was previously defined using dot products can now be extended to other type of vector spaces. We can now talk about the length of a function, a length of a polynomial, the distance between 2 matrices, the distance between 2 functions, the orthogonality between 2, let's say, polynomial, the orthogonality between 2 functions, the orthogonality between 2 matrices. All this thing can be now, it now makes sense, right? Okay, so for example, let's look at this. So in Rn, okay, this magnitude of these vectors, the length of these vectors is defined as a square root of the dot products, or usually we write it like this because, you know, we like square better than square root, so sometimes we write it like this. That's the length, right? And distance, how do we talk about distance? So distance between 2 vectors, right? You have u, you have v. So let's look at this picture. You have vector u, you have vector v. This is vector u minus v. So the distance between these 2 vectors is actually given by the magnitude of this difference of these 2 vectors, u minus v. And we talked about this before. Again, distance, right, is the magnitude of this vector, which is the square root of the dot products of these 2 vectors. This is the distance between that two vectors. And obviously we can also talk about orthogonality, right? Between two vectors. If two vectors, the dot product is 0, they are orthogonal, and all that now can be extended using the inner products, okay? Using inner products, okay? So for example, the length, instead of looking at dot products, now we're looking at this inner products, right? So if this is defined as v dot v, if we are in Rn, right, everything will follow. Everything will be the same as the one that we have before. So you will see that it is the same as the one that we have before. We can also talk about distance now, and we can also talk about orthogonality, right, using the general version of the dot products. So for example, okay, let's look at this vector space again, okay? So let's look at this vector space, C, okay, 0, 1. And this is a version of the dot products. We already verified that these operations actually give you an inner product, which is a generalization of dot products. And let's say if I give you the function fx equal to x and gx equals to 3x minus 2, and now we can talk about, hey, what is the length of these vectors, okay? Hey, what is the distance between these two vectors? What is the distance between these two vectors, okay? Hey, what is the angle, right, between these two vectors? We can take the dot products, right? So the dot products right here is going to be the inner products, and now we can do all this computation pretty easily. So for example, you can see that the length of this functions, right, the length of these functions, follow these definitions, right? Now this is defined as this. You compute that, you have that. So the length of this function is 1 over square root of 3. Okay, we are kind of like just using the dot products. So dot products, this is how we talk about the length of vectors, right? In Rn's, this is going to be the square root of v dot v. So now we don't talk about v dot v, we talk about v inner products of v and v, right? And the inner products right here is defined like this. So we can talk about in this generalized sense, right? In this generalized version of it, we can talk about the length of a function, the length of a functions, right? These functions, what's the length of these functions? Well, using these inner products, the length of these functions is 1 over square root of 3. What is the distance between these two functions? Well, using inner products, okay, take the difference between fx and gx, turns out to be this, right? So take the inner products, this is taking the dot product basically, do the computations, right? Turns out to be 4 over 3, right? So the distance between these two functions is 2 over square root of 3. Okay, see that we can do all that kind of things now. Is this two function orthogonal? Is these two function orthogonal to each other? Well, let's do the dot products, right? The generalization of dot products, which is the inner products. So compute the product of fg, multiply them, integrate them, and it turns out this to be 0. So now we know that, okay, this vector here, which is a functions, this vector here, which is again a functions, these two functions actually, they are orthogonal to each other. They are 90 degrees to each other. Now we can do that now, okay? We can talk about things like this now, right? We can talk about a functions and another functions. What is the angle between them? Are they 90 degrees to each other or not? Now we can talk about this. This is what math is about now. You see it? We did that before with the concept of vector spaces, from Euclidean space Rn to other type of vector spaces. We are doing exactly the same thing here. We're looking at dot products and expand that dot products to inner products, which now can be defined for all type of vector spaces. Doesn't have to be on Rn anymore. Okay? All right, so now we're going to do something even fancier. So we, last time using dot products, we can talk about the length of a vectors, right? We can talk about the length of a vectors. Okay, this is v dot v, right? We can talk about distance. We can talk about orthogonality. In fact, we are also doing something that's like this. Remember, we can talk about projections and stuff like that. You have a vector space W. You have a vectors V, right? How do we do the projections, right? So the projection right here, right? So the projection right here, this is called the projection vectors of V onto the vector space W. And how do we do that? Well, if we know the basis, we know that this space W have orthogonal bases. Let's say U1 and U2, these are orthogonal, right? These are orthogonal bases, right? If these are orthogonal bases, and then, okay, we define the projections of this vector v onto this vector space w as v dot u1, right, over u1 square multiply u1 plus v dot u2, right? These are typical dot products in Rn, right? Okay, you have something like this and stuff like that. Now, I'm just saying that we can also do the same thing now on vectors that is no longer in Rn, right? So for example, okay, I can be like, hey, I have a space, okay, this space is spanned by some functions, right? This space is spanned by some functions and they are orthogonal functions, right? So I have like f1, f2, okay, f1, f2, right? This f1, f2 here is orthogonal. Their inner product f1, f2 here is 0. And I have a function, let's say e of x or some other type of functions. Let's call it g. I want to see, hey, how much of that g is on the space? Again, nothing's going to change, right? This is going to call projections, right? Projections of g onto w. And what is it going to be? Well, this is a generalizations of the dot product. Everything that we do for the dot product will carry forwards, will carry over to here. So here this will be the inner product of g and the function f1, right, divided by the magnitude of this function square, right, the length, all right, and then we have f1 and then plus g, okay, f2, right, inner products f2 and stuff like that. We can do all that now. It's not a problem. We can also talk about projection now. So our projection last time is on Rn. Now our projection could be on any vector spaces. Same formula, same concept. Everything exactly the same. Nothing changed. This is the power of generalizing an idea that works for a small vector space like Rn, the things that we know, and then we expand it. How do we expand it? Well, we capture all the properties for the dot products, and we say is that, hey, now this so-called inner products, it captures all the properties of dot products. Everything you can do it with dot products, I can do it with this inner product because it's the same thing, right? It's the same thing, and that's the main idea here, okay? All right, let's recall a concept that we learned from before, all right? We are almost at the end, okay? Right, so this is a vector space W, right? So let's say you have a vector V, right? And we know that this is a projections vector. This is a projections of V onto W. We know how to compute that. Don't worry about it. And if you are looking at any other vectors that is on W, let's say you have this vector that is on W. If you look at this distance right here, this distance right here is definitely longer than this distance right here. So in fact, if you can, if you're looking for a vector W that is on this vector space W, the one that is closest to V is this vectors right here. So projection of V onto W is the one that's closest to V. Okay? All right. Now, let me tell you a story. Okay, let's look at this example right here. Okay, so the story goes like this. If I have a collection of vectors in my in my possessions, so let's say I have a W. What I have is constant value functions. I have my cosine of x. I have my cosine of 2x, right? All the way to, let's say, cosine of 100x, for example. I also have my sine x. I also have my sine 2x, all the ways to sine 100x, let's say. So altogether, I have 100 functions here, okay, and I have another 100 function here, and I have this function. So altogether, I have 201 function only. All right, so that's my functions that I have, and I can consider all their linear combinations, but linear combinations of this 201 function only. Okay, so most of the time, if you give me a functions like ex, right? If you give me a function like fx equal to ex, I don't have that ex in my collections. All my linear combination here cannot get ex. Okay, exponential functions cannot be written as a finite combination of your sine and cosine function. That's not possible. So my ex is out of the reach. Okay, my ex is out of the reach. I can't get it. I can't get my ex. So I can only find some w, some function that I have. Let's say this function is here that I have. Okay, this is a function that I have, linear combination of all these functions. And you look at this distance here. Okay, this function here is pretty far away from this. If you look at the projection vectors, again, if you look at my projection vectors, my projections of f onto w, this projection vector right here seems to have the shortest distance, all right? Seems to have the shortest distance compares to all the other vectors I have. You look at this distance here is longer than this distance. So if I can only use the linear combination of these 201 functions, the one that best approximate these functions is the projection vectors. You follow? The projection vectors is the functions that I have, because it can be written as a linear combination of all these vectors that is closest to this. So if you're looking for functions which belongs to my collections, these are all the functions that I have, the one that is closest to it is the projection vector f onto the space W. Okay, so this is a version of the least square approximation problems. If the question is, if this is the only things that I have, let's say your computer cannot store a lot of stuff, so you only store these 201 basis vectors. And if you give me some of the functions, I cannot write that functions as the linear combination of this, but I can write it as the one that is closest to it. So I want to find some things that I have that's closest to it, and we do these computations right here. And this computation is something that we know already, as long as we've been provided orthogonal basis. So if we are in this vector space, if we are using this inner products, okay, we are using this inner product, you can verify that all this basis vector here, all these vectors here are orthogonal. The verification is here, just some computations. And so these are all the things that are orthogonal. Everything that I have, everything that's in my possessions is actually orthogonal function. These are all the functions that I have is in my possessions. They are all orthogonal. And it turns out that if you have a function ex right here, let's say you have a function ex right here, okay, this is our ex, this is our ex, so on and so forth, or in general, just a function f, doesn't have to be ex, right? Just a function f. Then the one that's that belongs to my collection that's closest to this fx is given by the projections formulas. So this is a functions, obviously it's a span of all the functions that I have that's closest to it. So I have to identify all my coefficients, right? And all this coefficient here has been identified. Okay, the one that's closest to f, okay, is this thing. This is the one that I definitely possess. I have all these functions, and the coefficient here, all these coefficients here are given by this. So this is the one that I belongs to my collections that is closest to whatever f that you gave me in my example just now, that f is ex. So if fx is equal to ex is given, and all this thing can be computed, and you have numbers for this. These are all just real value. Right now I leave it as fx because it could be something that's other than ex. It doesn't really matter. I can provide a general formula for this. And this is a version of the least square approximation, which is very powerful now, as you can see, because we are applying it on the functions. We're not applying it to column vectors anymore. We can do exactly the same thing on function spaces now. And all these questions that I asked, what is the one that is closest to this? And all these questions are very important, because most of the time you don't have infinite collection of basis vector. You only have some of them. Like in this case, I only have 201 of them, and I need to be able to approximate all the function in the world using these finite resources. And we know how to do that because we know the projection vector is the closest to any function that is here, like projection vector. This one is the closest. We talked about this in the previous video also. And now we can actually compute all these projection vectors, okay? All right, so in the least square methods, because we have fundamental theorem of linear algebra, so we can write as a matrix and so on and so forth. We can't write it as a matrix here now, though, because we are no longer in Rn. So we're no longer in Rn. We don't have a fundamental theorem of linear algebra. There's no null space of a matrix, column space of a matrix. So our final answer is this. It's pretty cool, huh? All right, this is the end of the video, and I really hope that you enjoyed this course and you learned a lot from learn a lot of mathematics, especially abstract mathematics, and know what mathematics is all about by taking this course. All right, we'll see you in the future.